Number e is basically Euler's number. And what we do here with the number e is it's another way of working with exponential growth or decay problems. It's kind of the same scenario of everything we've worked on so far with growth and decays. The same rules are going to apply when we do our graphing. When we do the graphing with the letter e, or the number e here, it's actually even easier. It's basically just straight table work. You still will show your shifts. You still have an h and a k. But what you'll also use a lot of times with these e values is that you're going to have exponent rules as well. And those exponent rules don't change. So what I want to do is kind of quickly show you guys what the number e is before we get into it. And I find it, it's called natural base. And as we get into this more and more and more, we're going to start, the second half of this chapter deals with what are called logarithms. And natural base, logarithms, they all kind of go hand in hand. Where this comes from is this following, well, in this case, we're going to call this just a statement. Later on in math, you're going to look at this as a series, an infinite series. If you take take this parenthesis junk of 1 plus 1 over n to the n, as the n values get larger and larger and larger and larger, that number that it approaches is that 2.7194,463. Look, we're 675. We're televideo conferencing with a kid that's in Florida.
Nice. How's the weather down there?
81.
Oh, sweet.
You know what'd be awesome if she's in trouble?
It's not Amy Clark, is it?
No.
Wow.
I wish.
No, that's me.
I wish I was in Florida, but.
Oh yeah, I guess I do too now.
You're gonna leave it like that.
But oh.
This will take a second.
it's fun. That's pretty awesome.
That is awesome.
And so she's watching what we're doing.
From the beach?
No, we've already seen the pool. Yeah. Anyway, so what happens is the n value gets larger and larger and larger. It always approaches this. As you get into pre-calc, you will deal with more what are called limits, and this is where this stuff gets into. You're not going to see it you're not going to have to prove anything. You're not going to have to work through any of the real nastiness of this. But this basic setup here, you've seen with our when we did the compounding interest. Remember when we said it compounded semi-annually or quarterly? We had a formula that parenthesis part looked similar to that. That's where this comes from. Okay? Now, what happens with the e, this value of e, is that you're going to be able to substitute e in for this whole statement. And we do that quite often when we get into those compounded interest problems. So we're probably going to throw out some of the old stuff that we've done and go into this. All right? So let me walk you through what happens when you have this value of e. Like I said, you will see it with exponent rules, like e squared times e to the fifth. Just add your exponents, things like that. So this stuff doesn't really change. You can treat it as an exponent. It's just denoted as a letter instead. Kind of like what you did with pi. We leave things in terms of pi. Same idea. And yeah, and I. One of the things I do want to show you guys is on the calculator where e is. Oops, wrong button. So if you hit second division, there's E. Okay.
I remember when we educated ourselves to memorize a good amount of pi in sixth grade. We still remember a lot of it.
Nice. So that's where you see where the E comes from. Second division, and then the E button comes up. So as you get into this stuff, we're going to be able to do these. You're going to be able to simplify these expressions. So if you have e cubed times e to the fourth, you follow your rules of exponents because those e values are the same bases. So what do you do with the exponents? You add. Very good. So it's e to the second. When you have 10e cubed over 5e squared, once again, you always deal with your numbers first. Yeah, 10 divided by 5 is 2. And then you would have e cubed over e squared. E, numerator or denominator? Numerator. And you're done. Okay. And then lastly, you have 3e to the negative 4x all squared. What do you do with that squared term? Yeah, you basically distribute it into all two parts here. So you have 3 squared and then it's e to the negative 4x squared. So what's 3 squared? Oh, there you go. So you get 9, and then it's e to the negative 8x, and then is that negative 8x happy or sad? Sad. Where will it be happy?
On the bottom.
Or in Florida. And that's what you do. Okay? Does that make sense? You just treat the e value just like you would a regular exponent as you're working through your exponent rules. Okay? Now, the other thing with the value of e, like I said, we will be graphing these. But when you're graphing values of e, you really are only going to get one number that's going to work. Everything else is kind of fudged. Okay? Let me show you what I mean by that. If you go to your calculator, I'd like you to type in the y equals 2e to the 0.75x. Y equals. Now, in your calculator, since you guys have the newer operating systems, you might not, you don't have the newer one, do you? And do you have the newer one? All right. When you do your calculator, when you go 2 second e to the, does your cursor automatically stay up at the top there on yours?
Yeah.
Does yours do that too, Amy?
Yeah.
Okay. Well, I'm saying because I don't know if you have the newer operating system here in your calculator. Robbie, does yours do that? Okay. Oh, that's right. So you got yours all set up. Mine, I have to put parentheses or anything. So I put parentheses up for mine. 0.75x. Close it. And now look at your graph. And once again, you will notice that you have what looks like a exponential growth problem, very similar to what we did for the past couple of days. Now, when you go to plot this, is there an h and a k in this? No, there's no h, there's no k. So where is your horizontal asymptote? It's at 0. Very good. Your horizontal asymptote is still going to be at 0. And then, where do you think your y-intercept is? 2. That value of a, the 2, the number out in front of the e, is still going to be your y-intercept. So go to your table, and you just want to get some points to plot. We know that since there's no h, there's no k, that means your horizontal asymptote is at 0. And at 0, it's 2. At negative 1, it's about 1. At negative 2, it's about half-ish. At positive 1, it's 4 something. 2, it's up here. So here's your graph. What is your domain? All reals. Domain is all reals. And then your range is going to be, what was your?
All real.
Greater than that.
Greater than 0.
There you go. And that's what it looks like. So the only thing that's going to change here is that instead of having maybe 1 or 2 or 3 points that you can actually physically plot, like we did with exponential growth and decay, you're really not going to have anything that makes any sense for your plotting points. The only one that will make sense is your y-intercept. Okay? Questions so far? All right. Let's look at one with a shift. So I have y equals e to the negative 0.5 times the quantity x minus 2, all plus 1. So when you have something like this again, your a value is the number in front of e. What's your a value here? 1. Your h and your k's, well, what's your value of h? Yeah. Your h is what? 2, and your k was 1. All right? So that means once you, what do you think your parent function is going to be when you plot it? What's that? No, I didn't hear the whole part. X, yeah, exactly. So when you go to plot this one out, the first thing you do is you plot your y equals e to the negative 0.5 to the x. You plot that out. Oop, we lost her. Should we just wait for her to call back? Now, we go to plot this, and then you just go ahead and shift it. So go to your calculator and type in y equals e to the negative 0.5x. And graph it. I always do the graph first when I'm dealing with these E ones, because sometimes if I don't put the parenthesis in the right spot, it'll be a straight line, then your graph's all screwed up. So now I just look at my table. So at -3, I'm at about 4.5. At -2, I'm almost at 3. -1, I'm about 1.5. 0, I'm 1. 1 on here, and I'm just scaling down. So this is my generic. Where will my new asymptote be at? 1. Your new asymptote is always at your value of k. And now with all of these points, what am I going to do to them? Shift them to the right because h is positive, and up 1. Over 2, up 1. Over 2, up 1. Over 2, up 1. Over 2, up 1. And so on. What is your domain? All real. And your range is all real except that are.
So wait, will domain always mean all real?
In these things. Yes, ma'am.
So the parent function for this is always using to know what numbers are in the next.
Yep. Always. The parent function is always going to be this. Yes, sir. Domain is your x values, your range are your y values. So in this case, the x values, there's nothing that tells you that an x value can't occur. The y values, since there's an asymptote, means it's either going to come towards that from top down, or it's going to come towards it from bottom up. Since it's coming from top down, that means it's going to be all the real numbers that are larger than it. Does that make sense? I guess she's too cool. Or if she had a diaper, she had to change. I knew I smelled something. Or was that Jeremy? Sorry. Ooh, that's on tape too. Hey. That's true. Questions about this? All right, let's look at the stuff then when it deals with the word problem. Now, once again, don't write all this out, okay? Just remember that we dealt with this formula before. Remember when we had the number of times something was compounding for X amount of years. So if it compounded quarterly, we would use N was 4, T for a number of years. Now instead of doing this, when we have accounts that what they're called continuously compounding, we use this. We're going to use the amount is going to be the principal, e to the RT. So A is the amount. Yes, hurt is good for your hair. It's good for dandruff. Your P is your principal. Think of the principal is the initial amount. Okay, the principal is the initial amount that you put into the account. The E is the button on your calculator. The R is your rate. And what do you always convert your rate to be? Decimal. And then the T is usually your time in years, or it'll tell you what it is. That's going to be your time. Okay? So as you go through these style problems, instead of it saying that we are compounding continuously, like semi-annually, things like that, it'll say continuous now, and it'll just look like this. You're depositing $1,000 into an account that pays 8% annual interest compounded continuously. What's the balance after a year? So, what is your initial amount? Your principal? 1,000. What is your rate? And then in this case, it's asking you for how many years. So as you substitute into the equation, you get 1,000 e to the 0.08 times 1. Just use your calculator. $1,000 e to the 0.08. Did you guys all get $1,083.29? Okay. How much do you have after 7 years? You get $17.50 and 67 cents. You guys remember the movie Office Space?
Yes.
Really? You've never seen Office Space? Watch Office Space. When they're talking about the scam they were dealing about stealing the rounded off little decimals of money. These are little itty bitty decimals of money. Thousands, hundreds of thousands of cents. They all go somewhere when you round. So they just tried to round them all together into their own little bank account. And they had to burn the house down.
Isn't that like a D word? What's the
Can you see my statement?
No.
There's quite a few of them, and a lot of them are not going to stay in school. Yes, yes, that one's in there.
It was.
All right. So this is the style stuff that we're going to deal with the word problems. Like I said, these word problems are really quite simple. So try this one. You are looking at a model for endangered species. Since 1972, the U.S. Fish and Wildlife Service has kept an endangered species list of endangered species in the United States for the years from 72 through 98. The number of species on the list can be modeled by the following blah, blah, blah. So, your initial amount of endangered species, or if whatever they call it, the principal amount here was 119.6. I don't know where they got the 0.6. Maybe it was like a six-legged something that only had 4 legs. Never. E to the 0.09117. So the number. What was the number of endangered species in 1972? 119. Your time would be 0. Anything with the 0 power is 1. Okay on that? Okay. Now, after it gets into, you remember when we did the stuff where you had to estimate how many years it took to have a certain amount of dollars or whatever? What did you do with your calculator to figure that out? Yeah. Yeah, exactly. Go to your table. So what I want you to do is put this into your graphing calculator. Let's see. It is 119.6 e to the whatever. 119.6 e to the 0.0917x. And go to your table. Now, they're asking you to figure out when the number of species reached about 1,000. So that means you just have to scroll through your table to figure out how many years have elapsed. So as you do that, about how many years have elapsed? So between 23 and 24 years, everybody agree on that? So if this started in 72, 23 to 24 years would be about what, 90, 95, 96, somewhere in there? Does that make sense? See how it's basically the exact same thing we've done earlier, it's just a little bit of a shift of the equation. Okay? Questions? Yes.
Oh, there
Letter E. Letter E. Letter E. No, I'm not watching anything on YouTube anymore.
Now you did enough videos.
My videos are awesome. No. Do those, please.